Thank you. Thanks for the invitation. It's my great pleasure to be here. And also thanks for the introduction from Dr. Chen. Okay, so basically today I have two lectures. So the first lecture will be something related to my PhD, but I try to make it easy to understand because I know today we have a mixed audience from bachelor all the way to PhD. I just try to mix the research part and also some lecture part for this two topic. So the first topic is actually related to the term we call it transportation network modeling. Maybe this is familiar to some of you, not very familiar to some of you. This is a large community, I have to say, in Hong Kong or in US. Basically, we try to model the transportation system in a network. We call it transportation network modeling. So we're talking about some basic knowledge in this area. And also, we're talking about some new developments. So here, basically, we're talking about the computational graph, how we can integrate the data with the network modeling technology. Okay, so let's first start with some motivation. So this is actually some lecture slides from my lecture, my lecture in Hong Kong. So why the question we want to answer here is why do we need the network modeling? So what is the motivation here? So it starts from a very basic question. So basically, we are, as a transportation engineer, the first thing we are doing is we build roads. We need to design how to build a road, and basically there's two community, and how do we build a highway or major road, so we want to connect them. So basically, here you can see this is a layout in Hong Kong. This is the highway in Hong Kong. And this is basically the main plan in the mainland China. So you can see that they try to develop this main line that connects different large cities. And if you look at the United States, it's also very similar. So you have the interstates in the blue color, and also you have some major road in red color. So in general, you can see that in every country, in every district, that you have some road network. But the question is, for example, in the future, you want to build a new road, then how do you decide whether you want to build a highway or it's a major road, or how many lanes, 2 lanes or 3 lanes, and what's the speed limit? So you have to make all those decisions. So that actually gives you a problem. We call it a network design problem. So this is the very beginning of this whole story. So this is actually a very interesting video I want to show you. This is actually a Nature paper. What they are doing is that they find that nature, the bacteria.
One classic example, Japanese are so clever at this. There's a slime mold, called Physarum polycephalum. And they had and this slime mold is very, very good at navigating through mazes and challenges. I mean, first to food wins. The conservation of energy, is rewarded. So how they set this up? They did several experiments. So the most fun one is they designed a nutrient, basically a nutrient-like maze, replicating Tokyo in the Japanese subway system. And so they started with Tokyo. They put oats, which is a nutritional source. They inoculated what is on this basic aggro map with all the major cities, the nodes around Tokyo. And then each of those nodes had a piece of oat on them, which was a source of nutrition. The main oat was where Tokyo was. They inoculated it. And then they let the slime mold then grow. And first it grew out randomly, exploratorily, just like you would do if you're a hunter or something, or hunting on the landscape looking for things. And then after about 28 hours, it reorganized itself in the most efficient way possible and reorganized the Japanese subway system.
Okay, so basically this video says that you just put those food in some important community, and then you let the slime mold, which is basically some bacteria, to explore itself. And then finally you see some network, and this network will be very similar to the road network or metro network in Tokyo or in France. Okay, so basically it says that there is some theory underneath this network design, and then we have to model it. Okay, so let's start from a very simple example why we need this model. Basically, the model we are talking about today is called traffic assignment. Maybe some of you learned this before, some of you not. The traffic assignment model is one of the most important model in the network modeling. Basically, it tries to assign the traffic demand to the network. Okay, so we try to understand what is the congestion, what is the traffic state on the network. Okay, but the question here is why do we need this? Why do we need this kind of very complicated mathematical model to do this? So let me give you a very simple example. So here we are saying that we have two cities A and B, and then we have one highway that with some heavy congestion. Okay? And then the governments, they want to do something because there's a congestion. Then let's say we try to widen the road. So basically, say for example, we just add one more lane to make the road more wider. Okay. So basically, when we increase the capacity, you can see that you have a wider road. Then we believe that this can make the traffic flow move more freely and then reducing the congestion. So basically, that's what we want to expect. But the story really this simple. So actually, what we have here is that it's not just one single road from city A to city B. In the real world, we usually have another road, like in this red one. Okay, so if you have some congestion on the green road, and then those drivers, they believe that there's a congestion, then they may move to the right road. Okay, because they always want to reduce their travel time. If they find that another route is shorter, then they want to move to another route. Okay, but later you find that so we widen this road. So this road becomes wide, and then it becomes less congested, right? And it becomes less congested, then the travel time becomes lower. Then you can imagine some people from this right road will move back to the green road. Okay, so does that really reduce the congestion? So how much it is reduced? It's actually unclear because the transportation network is actually a complicated system. So if you reduce the traffic congestion here, some people may come. Okay, so that's the issue. So basically you can see that some drivers have diverted from the red route to the green route. Okay, and then the green route becomes congested again. Okay, so that's the issue. So here you can see that this is what we expect, but there's something missing that we haven't modeled this whole process. So what is missing here? The key item we haven't considered is we call it a traveler's behavior or driver's behavior. So in general, we have an assumption here when we do this kind of modeling. The assumption is that the travelers, they always want to seek for the shortest path. Okay, so they are actually dynamic. Okay, so if they find there's a better route, then they will switch. Okay, so this is also called a rational traveler's assumption. So meaning that the travelers, they are rational. If there's a better route, then they will do it. They will take it. Okay, then these travelers, what they can do is that they just choose a different route. Okay, then in the real world transportation network, what is happening is actually an interaction between users and network. We call it demand and supply. Okay, the supply is actually the network. So you have different road, highway, main road, and local road, different capacity. And on the other hand, you have travelers. Travelers, they always choose some shortest path in the network. And because they choose the shortest path, and then this path becomes congested. And then it becomes congested, the travelers, they may reconsider their decision. Okay, so this becomes an iteration. So you can see that we are seeing that the traveler's behavior, they affect the traffic condition. And at the same time, the traffic condition will also affect the traveler's behavior. So this becomes a loop. Okay, so how do we solve this loop? Basically, we need to understand what is the traveler's behavior and what is the network performance. And you combine all this together, so you solve the traffic assignment, or we call it traffic equilibrium. And this is a key idea in the network modeling in transportation. Okay, so let me give you a very simple but famous story here. It's called Breast paradox. I think maybe many of you heard about it. Just quickly go over the setting. So in general, you can see that you have two cities, A and B, and then you have two different routes from A to B. Okay, so in the first route, this link, you have a link performance function. We call it x over 100. Basically means that if you have one person using this route, then the travel time is 1 over 100 hours. If you have 200 people using this road, then the travel time will be 2 hours. Okay, and this road is constant. You can imagine it's a super good highway. Okay, so it's always 1 hour. Okay, similarly, another route is actually symmetric. You have 1 hour and x over 100 hours. X is the number of drivers using this route. Okay, so given this setting, so say for example, we have 100 people want to go from A to B. Okay, so how do they choose their route? So you can see that this two route is actually symmetric. It's identical. Then what they will do is basically 50-50. Right? They just split even. And then you can see everyone on this route, the travel time will be 50 over 100 plus 1 hour. So it's 1.5 hours. Okay, so this route is 1.5 hours, this route is 1.5 hours. Okay, so the average delay is 1.5. Okay, and then let's say the governments, they want to do some good things. They want to build a highway to improve the connectivity. So what they're doing is basically they build this highway. This is a super highway that is super fast. Let's make it extreme. We believe that the travel time is almost zero. Okay, so we have a zero travel time highway connecting these two nodes. Okay, so basically we build a good road, right? We spend money, we build a good road. Then we expect that the traffic conditions should getting better, right? So that's what we expect. But if that's true, let's see. Okay, so you can see that given this whole network, if you are the first driver, which route you are taking? So now you have three options, right? The first option is this one, the second option is this one, and the third option is a new route. It's this zigzag. Okay, so what's the travel time for the first one? It's 1 over 100 plus 1, right? 1.01. And this one is also 1.01. But the travel time for this zigzag route is just 0.02. Okay, so this is the shortest. So if you are first driver, you'll definitely take this route. Okay, and if you're a second driver, you can keep calculating. So this one is 1.02, 1.02, but this one is 0.002. So basically, the second one is also taking this. Okay, so if you keep doing this, you'll find that all these 100 people, they find that the third route will be the shortest. Okay. Okay, so all those 100 people were taking this route. Okay, and then what's the travel time on this route? So 100 over 100 plus 0 plus 100 over 100, so it's 2 hours. Okay, so you can see that after you're building a super good route, the average delay for all those peoples become 2 hours, so it's increased. Okay, so this is called Breast paradox. This is super popular. So this actually gives you the implication that as a government, it's not always good to build a road. So sometimes you build a road, you don't consider the traveler's choice. That actually congests the city, makes the city the traffic condition even worse. Okay, so that actually motivates our problem at the very beginning. When we want to design a road, it's not just simply you find that somewhere is congested and then you just try to widen the road or you just build a new road. It's not like that because there's kind of Breast paradox. Okay, and there's actually many studies in real world. They try to look at different cities, and in different cities, the Breast paradox actually exists in the real world. Okay, so that basically means you have to have some model to guide you how to design the new road. Okay, so you can see that basically adding a fast road on the network is not always a good idea. sometimes it makes the network become worse. The issue here is that drivers, they won't listen to you. The drivers, they always choose their best route. Okay. So how do we evaluate whether a new road is good or not? Then we need a model, and this model we call it a network modeling or traffic assignment. Okay. So this is the beginning of the story. So, if you look at United States, actually in the United States, every I would say for each of the states or 2 or 3 states, usually they have a planning organization. Oh, they call it MPO, Metropolitan Planning Organization. And then those this planning organization, they are maintaining a traffic network model for this whole area. And if there's a major construction, for example, they want to build a new bridge or they want to build a new road in this area, then they have to evaluate on this model. Okay. So similarly in Hong Kong, in the transport department, they also have a planning model. I think they call it CTS, a comprehensive transport survey model. So basically, if you want to have some new construction, you have to pass this kind of feasibility test on this network model. I think similar story happens in Korea. I'm very sure about detail. I just heard this story from Professor Chen that you have to do this kind of check before the actual construction. Okay, so actually a lot of consultancy companies, they are doing this all the time. Okay, so here let me give you some basic of how to build this model. Okay, so the network modeling is actually a very large community. I cannot cover it for today or even for one whole week. It's too many things, but I just try to give you the basic notation and the key idea here. And in general, we call it a traffic network modeling or transportation network modeling. This whole area, we want to quantitatively model the variables in a transportation network. Okay, so this network can be road network, and can be transit network, or it can be multimodal network. So as long as you are talking about some network in transportation, and then basically we can model the variables on the network, including speed, flow, density, or travel time. Okay, so the purpose of this model is try to replicate and understand the traffic conditions in the real world. Okay, so you have a real world network, and we build another network in our computer, and we want to use this computer model to replicate or mimic the real world network. And then we can understand why there's a congestion and why people choosing this route. Okay, given this, then you can make the design, and you can work on this. You can work on some construction plan. Okay, so this is actually a very large community in the transportation research area, and in TRB, Transportation Research Board, there's a committee, AEP 40. So basically, if you check this website, you can Google it, and you look at the people here. So basically, they are, if you check their name, basically they are many of them, they are working on this area a lot. Okay, some popular, very famous professor, for example, the professor in Northwestern, Hani Mamasani, the academia. So basically, he is also working in the network modeling area. Okay, and I think many professors in KAIST from UC Berkeley, and D'Agenzo is actually I think he's the establisher for this whole community. Okay, so let's starting from some notation. Okay, so some very basic notation to help you to build a model in the network. Okay, so in general, the first thing is that given, let's use road network as an example. So if you are talking about transit network, the idea is similar. So here, let's say we have a road network. We model it as a graph, and the graph has V as vertices and E as edge. Okay, so V is representing the intersection. Okay, and edge representing the road. Okay, so basically each intersection is a node and each road is an edge. So you're building a road network as a bidirectional graph. Okay, and then you consider, we call it OD pair, origin destination pair. So you have origin R and destination S, and R and S is just a node in the graph. Okay, So basically we say we have an OD pair RS. So say for example we have OD pair A and D, AD. Okay. So in general we assume that we have some people go from R to S. We call it a demand, OD demand or OD flow. Usually it's represented by Q. Okay. So Q sub RS, QRS representing the number of people go from R, let's say QAD, then it's number of people go from A to D. Okay, so this is a demand. And once you have the demand, the second thing that they can actually choose different routes. Okay, so for this network, it has 3 routes. So ABD, ACD, and ABCD, right? So here we are referring to, for each OD pair, we have several number of passes. Okay, and this KRS refers to the set of paths from R to S. Okay, and then you have the path flow, FRSK, basically saying that the number of people go from R to S using path K. Okay, so here we have K equals to 1, 2, 3, referring to, so you can, the order doesn't matter, so you just define an order yourself. So here I'm saying that the first path is ABD, second path is ACD, and third path is ABCD. Okay, so then we have this equation. So you sum all the paths for this OD pair, you have the total OD. Okay, very easy to understand. So the OD flow, you decompose it into different path flow. Okay, and the path flow is actually determined by the choice. Okay, so we call it PRSK. So basically PRSK means the probability of choosing path K. Okay, so here basically you can see that we sum over all the paths, it gives you 1. Okay, so this the summation of the probability equals 1. And then you have this equation. You have Q, the OD from R to S, multiplied by the probability choosing path K equals the path flow RSK. Okay, so then you can calculate the path flow for on this network. And then given the path flow, you can actually calculate how many people are using each of the road. We call it a link flow. Okay, so link index we set it be A, and then we have a VA or XA. So some paper using VA and sometimes some paper use XA. So basically it refers to the link flow on each of the link. Okay, so this is a little bit tricky. So basically the link flow on one link is a summation of the paths that passes this link. Okay, for example, if you look at the link AB, the link flow on the link AB is so you have 3 paths. ABD use this link, ABCD use this link, and ACD don't use this link. Right? Then basically the link flow XAB equals the path flow ABD plus the path flow ABCD. Okay, so then this what is mean here? So this indicator we call delta. Delta RSKA refers to whether the link the path RSK use link A or not. If it uses the link A, then it's 1. Otherwise, it's 0. Okay, and this quantity is only depending on the network topology. So once you have the network, you have delta. So it's not an unknown variable; it's a known variable. So this one can be calculated before the whole modeling process. Okay, so you have F times delta sum over path, sum over OD. Okay, so you have the link flow, and the F you can plug it in. The F also equals to P times Q. So this is the final equation you have that connects from OD all the way to the link flow. Okay, so basically you have the OD, means how many people want to travel, and you use 2 indicator, delta and P. Then finally you know how many people are on each link. Okay, so given this, and then you have the link flow, right? And then we assume a link performance function. We call it a link performance function on each of the link. So basically, our expectation is that you have more people on the road and then you have a higher congestion. Okay, so something we have is like this function. So basically, at the very beginning, if not too many people are using this link, the travel time is similar. And if more people using the link, then you can see that the travel time increase a lot. So this function is serially monotone increasing. Okay. So the one that we use very often is called BPR function. I think you heard about this a lot. The BPR function is basically like this, and is like this shape. So at the very beginning, it's stable, and after the VC issue greater than 1, you can see that the travel time increase a lot. So this actually translates the number of people using the link to the congestion on this link. Okay, so once you have the link travel time, so now you have the travel time on each of the link, and then you can recalculate what is the travel time for one pass. For example, the ABD is basically the travel time for AB plus travel time BD. Okay, so you can recalculate a pass travel time. We call it CRSK. Okay, so basically it refers to the travel time for this whole pass. Okay, of course you can add some new factors. For example, if on this pass you have some toll, then you just add a toll, and if you have some traffic signal, then maybe you can add some penalty. For example, the turning movement cost or the time for waiting for the traffic signal, and you just put it here, and then you can have some generalized travel cost of the route. Okay, so usually if you have multiple components, we use some coefficients, alpha and beta. We convert everything to money. Okay, for example, this one we have travel time plus distance plus toll. This one is actually used by Uber, right? Uber basically calculates the charge based on this equation. So basically, they convert the time to money, and then they convert the distance to money, and then they have some additional toll. Okay, so alpha and beta is basically some coefficient that you can obtain from the survey. Okay, so you have the travel cost, past cost, and then finally, given remember that the travelers make their decision based on the travel time, based on the cost, right? Then finally, we define a behavior function here, psi, and the psi, the input will be the cost, and then the output will be how many people will choosing which route. Okay, so we call it a behavior function. I think you definitely learn about the logic model, probability model, all those belongs to this whole gerund. So basically, it's kind of a behavior model. Okay, and basically, if you use different behavior model, you have different traffic models. So for example, there are several popular ones. The first one, we call it a user equilibrium. The user equilibrium, the behavior model says that each traveler, they know the precise travel time, and then they will always choose the travel time with the smallest cost. So this is an assumption for the user equilibrium. And if you look at the stochastic user equilibrium, then that basically means that so the travelers, they still want to choose the shortest path, but what is different is that they only know a distribution of the travel time. So they have some, their knowledge has some error. And because of this error, they cannot determine which route is the shortest. What they can do is that they only select the shortest path based on the probability. Okay, and there are actually many others like system optimal and reliability-based stochastic user equilibrium. This is by Professor William Lam, and I think basically if you name the professors in the network modeling community, each of them has some representative model in this area. There are so many, so I won't list it here. But in general, we just use this equation. So in general, it's a function that reflects the traveler's action based on the travel time, based on the utility. Okay, so now we have everything ready. So you can see that this whole story is like this. So at the very beginning, you have the OD. You have the how many people want to travel. And then based on how they travel, based on the travel cost, the OD and travel cost, you can calculate which route they are taking. Then you get the path flow. And given the path flow, you can calculate what is the link flow. Okay? And given the link flow, using the link performance function, you can calculate what is the congestion on its route. And given the the congestion on its road, you can calculate the travel time for each of the paths. And the paths will in return affect the people's choice on the network again. So you can see this becomes a loop. Okay, so we formulate this problem as a fixed point problem. Okay, so if, for example, if we solve this whole system, then that means all those errors hold, all those equations hold, and then we call this becomes a equilibrated state or stabilized state. And this equilibrated state, we call it a traffic equilibrium. Okay, so given different travel behavior, the equilibrium will be different. This is because the traveler's behavior is different. And why this is important is because we believe that our daily traffic, for example, today's traffic in Jeju or in Seoul, it is in equilibrium. Okay, because it's a normal traffic, so every day the traffic pattern is similar, even though there are some fluctuation, but the daily traffic, the morning, in the workday, or in the weekdays is similar. So we believe that it's some kind of equilibrium in each of the city. And then we try to model this kind of equilibrium using this whole schema. Okay, but in this schema, you have to determine how many people travel. This is the first thing, demand. And how people react to the past cost. Second thing, behavior. Okay, and also how the link flow makes the congestion, link performance function. So this is the three key components in this whole network, in this whole system. Okay. Okay, so here is some challenge. So basically, given this whole modeling framework, you can see that we are given a network, and this network is usually correct. So it's nothing wrong for this network. And then what we need to assume is three parts. We need to assume a OD. We need to assume a link performance function and a choice model. So usually choice model can be done from a survey or OD from a survey, and the link performance function, you just look at the road, you draw the fundamental diagram. You have the link performance function. And then given these three, we can expect that we can model the traffic, and this traffic assignment model actually replicate the real world. Okay, if we can do that, then this model is good enough. We can use this model to do prediction. For example, in the future, we want to build a new road. We just add a road and run this model again. Okay, so this is the whole idea for the network modeling, and that's why it's used for. Okay, but there are several issues that I want to talk today. So this is more research part. So before this slide is actually lecture notes. Okay, after this slide is more like research part. If we want to make some contribution or do some research in this area, so there are some questions we haven't addressed. So there's no guarantee that this model replicates the real world. Okay, and also basically in the real world we have a lot of data. How can we use this data in this model? It's unknown. Okay, and then we move to this part how we can make contribution. So before that, let me quickly give you a review of the neural network, because I think most of the people here are very familiar with AI parts, so I do it quickly. Okay, so here you can see that so we talk about neural network. So neural network is actually a deterministic multiple to multiple function. You just think of it as an arbitrary function, right? For example, if you want to do a digit handwriting recognition, basically your input is a pixel of each cell, and then your output is just a 10-dimensional vector. Okay, so basically you can design your neural network arbitrarily, right? So any input, any output, you can just flexibly organize the neural network module. Okay, and then I don't need to talk about this. For a simple neural network neuron, what you have is just some weight. Okay, so you're just trying to adjust the weight to make this neuron works better. Okay, and if you have this multiple layer, and you can see, I think you definitely know that the neural network, when it's evaluated in your computer in GPU, is actually vectorized, meaning that you don't calculate each neuron separately. What you are doing is actually you are doing a matrix calculation here. So you organize all those weights into a W matrix, which is a weight, and you have some bias matrix. And basically, you just when you evaluate the forward path of the neural network, it's just some matrix calculation. Okay, and this matrix calculation is very fast in GPU. Okay, So the backward is also very straightforward. You just use chain rule. Okay, so as long as your forward path is differentiable, and then you can, each module is differentiable, and then you can easily make use of the chain rule to take the derivative of each function. Okay, so here I try to make the concept of neural network a little bit larger. So we see that there's another concept called computational graph. Computational graph is actually a generalized definition of a neural network. Basically, we are saying that when you do the auto differentiation in the neural network, it's actually automatically construct a computational graph. A computational graph is basically a DAG, a directed acyclic graph, and then you have each of the nodes being variables and the edge referring to the data flow. So you can see that this is a neural network, but you can represent it as a computational graph. Okay, so if you understand the implementation detail in the PyTorch or TensorFlow, basically they are doing this. Okay, so when you write code in the PyTorch or TensorFlow, what they are doing is that you can see that they put each of the tensor into a node, and then all those nodes they basically connect. For example, you can see XW, they multiply together here, and then you take a ReLU, and then you multiply by another weight. So basically, this is one MLP. This is another MLP. Okay. So in general, you can reorganize your neural network as a computational graph. Okay. So in this computational graph, the forward path will be evaluating the model. Okay. So basically, it's the forward iteration in the neural network, and the backward is basically you calculate the gradient for each of the variable. Okay. So so in our view, computational graph neural network is almost identical. Okay, we just use another term. Okay, so why we are talking about this is that we are saying that the network modeling, so all the notations I showed you before, can actually be cast into a computational graph. That means you can use a neural network style to do the network modeling. Okay, so here we are saying, first thing, we need to vectorize all the variables I just mentioned. Okay, so firstly, I'll try to give you some handwriting here, but it's okay. I think you can definitely do it yourself. So first, you can formulate the OD QRS as a long vector. Okay, and then once you have this vector, so firstly we have this, right? So P times Q equals F. But you can smartly organize your P as a matrix. Okay, and then you have a Q as a vector times the P matrix, then you get F as a vector. F becomes the path flow. Okay, and the delta, if you still remember delta here, which is the indicator whether the path uses link or not. You can also reorganize this delta as a matrix delta, capital delta. Okay, then your path flow multiplied by this delta, you have the link flow. Okay, so everything can be vectorized in the network modeling. So you don't need to write all those summation equations. What you can do is just simple matrix calculation. Okay, and then link performance function here is just each of the link vector x. You just apply a function very similar to ReLU, but this time it's not ReLU, it's a BPR function. And then you have the travel time. Okay, so once you have the travel time, you sum it, you get the path cost, right? So here you are using delta, and this part you just use the delta transpose. Okay, you can revert it and you get the path cost. Okay, and then finally your raw choice model becomes precise, so you can calculate the P. Okay, so that means in the network modeling part, you can actually reorganize it into something like this. So the traffic assignment becomes a forward iteration. So at the very beginning, you have the OD. Okay, and then you apply some raw choice model, you get the path flow. And the path flow, you multiply by the delta, you get the link flow. And the link flow, you apply some BPR function, you get the link cost. Okay, so you can see that the evaluation of the so basically the traffic assignment becomes a forward, and you want to make it an equilibrium, right? And then you can go back. So So that means the fixed point problem, you can reformulate it as a forward and backward iteration. And if your forward backward can converge, the fixed point, basically you find the stabilized condition. Okay, so that's one key idea. So basically we try to connect the idea in neural network with the network modeling technologies. Okay, so I skipped this part, which I plan to do the handwriting. Okay, so then why this is useful? So let me give you a setting. Okay, so the setting is as follows. So here you have a network. This is a Pittsburgh actually, and then you have multiple data sources. For example, you have some traffic counts, you have some incident, you have some parking occupancy, and you have some trajectory data, and you have all sorts of data. But even though you have a lot of data, but some area is still unobserved, and the data actually only covers part of the network. You don't have a full picture of the network, right? So in general, what we have now is like this. Each of the data source give you part of this whole elephants, but you don't have the full picture. And what we want to do is that we want to integrate all those data source into one single model, such that we can have a full picture of the network. Okay, so then what we can do is that, for example, you can organize your data from the regional level all the way to row level. For example, you may have some attraction production data. This is mainly from the census data, and also you may have some check-in data or event data that can reflect the OD, or you have some trajectory data that can be raw choice, and you have traffic volume speed that is link level data. Okay, so if you have all those data and you map all those data with the computational graph. So here, this is the original computational graph for the traffic assignment model. And what you can do is that you may have some observed flow, you connect it to the flow. And you may have some speed data, you connect to the speed. And you may have some historical OD, you connect to this OD. And basically, we believe that these two should be similar. Your observed data should be similar to your model, right? Then you can build a MSE loss, mean square error loss here, and here, and here. Okay? So because the neural network or computational graph, you can do the error back propagation, right? So you can calculate a gradient. For example, you check the speed here and check the speed here. And then you calculate the error and you back propagate this error all the way to this network. And then you can calibrate OD, you can calibrate the raw choice, and you can calibrate the path flow. Okay? So basically, when you insert all those data into the computational graph, and then you can make this system consistent and a holistic model. Okay? So that's an idea we want to propose this model. And here I just give you an example. So what you have here is a Pittsburgh network, and we have multiple sources of the data. You have the planning model from the planning agency, and you have some traffic trajectory data, you have travel time data, and also the volume data. And you can see that this model is, this system is very large. So we are doing 5 hours and every 15 minutes. Okay, and for this whole network, you have 80K OD pair. Okay, you have 16K links. So it's a super large network. So because we are using the computational graph, and the computational graph actually is neural network, that means we can use the learning algorithm in the neural network. For example, the ADAM, ADA grad, ADA delta. So essentially you can see that if you are using some more advanced gradient descent method, it can improve the accuracy. And also at the same time, we can use GPU and multi-core. We can use multi-processing, which also accelerates the solution time. Okay, because this whole network is so large, it actually takes a long time to solve. Okay, so finally we just plot this figure. So this is the x-axis is estimated, observed travel count. So for example, we have multiple sensors on the network. Okay, so each of the sensors it gives you the traffic flow, and on the other hand, we have the estimated one from the data, from the model. So if all those data points is along this xy line, then means our model is perfect. So this one, you can see that it's still not good enough. So the R square is 0.6 or 0.7 something. But this is already the state of the art for large scale network because this is a super difficult problem. Okay. So in general, let me summarize quickly what is the advantage for this kind of new modeling technique. So we are talking about the computational graph. Basically, we are saying that it's a good way to combine model and data. Okay, so the model is that basically the forward path is a traditional traffic assignment model, and the backward is a error propagation based on the observed data. And it can solve the large scale network because it's gradient based, and it has parallel computing and GPU based computing, and also you can use the advanced solution method like Adam and AdaGrad. Okay, and also it integrates the multi-source data. So basically this becomes a solution schema. So basically you have some decision variable, and then you try to build a model, and finally you have some objective, and also you insert some data. Okay, and then you just do the error propagation. You can calibrate this whole model, and you integrate the data and model together. Okay, so this is the whole idea for this computational graph, and I just want to add some more things for the further development. The computational graph is actually reflects an idea of differential programming. I think some of you might heard of this term. Differential programming is proposed by Hinton. Hinton says that we are not doing deep learning, we are doing differential programming. Differentiable programming means that we are building a model that is differentiable. As long as it's differentiable, then you can calibrate it very easily. Okay, so that also means that any module, if it's differentiable, you can put into the computational graph. For example, the recent two hot topic. One is the smart prediction optimization. Another one is PINN, physics-informed neural network. It's basically putting some new things into the neural network, but this part, the new module is still differentiable. Okay, so it's the same idea. For example, I just want to talk about a recent study what we are doing. Basically, we are doing a vehicle relocation problem, and what you are doing is that you are predicting the vehicle location, and then you distribute the vehicle based on their future location. So you can see that it's a prediction plus optimization problem. And you can put this optimization and prediction all the way into this whole framework. Okay, and it's still a computational graph, and you can do the forward passing, which is evaluating the distribution of the network of the vehicle, and the backward is to calibrate the optimization model and prediction model. So this idea can be applied to different areas. Okay, so lastly, I just want to list out all the papers that using computational graph in different areas. So what I show you is just one example, but the computational graph is actually a generalized learning scheme. For example, the first paper is in 2018 by Professor Xuesong Zhou in Part C. So basically, he first time used computational graph in the 4-step model, in the transport planning model. And then I did something in the OD estimation. And then 2022, Xuesong Zhou actually with his Korean students, King, I forgot the first name, sorry. He also extended this model into behavioral learning. And then there's one more paper on the traffic state transformation on a highway. And also there's, we can also use computational graph to do the travel time estimation. And there's one more, this is an independent scholar working in Beijing. They use the same modeling structure to the transit network. And also recently, there's a paper from my advisor. They are doing user equilibrium. Okay, so the content I'm showing today is mainly this paper and this paper. Okay, and also my paper. Okay, so it's just give you a very quick overview of this modeling technique. If you are working on any of this direction, you can try to read this paper, which might be helpful. Okay, so that would be the first talk. Hopefully I keep the time. Okay, thank you. If you have any questions, let me know.
Any questions from the students? Questions?
If I may. Because, well, just to say the question from the student, so I could. Well, can I? Well, actually, I want to make some, well, maybe stupid question, maybe easy level question, because I'm not on this field, so I just have a simple question. So link cost and the weight, that's the same concept, right?
Link cost.
Link cost and the weight in the machine learning thing.
Yes.
Yeah.
But one is learnable, another one is not learnable. That's
Yeah, that's different, but basically the concept is the same.
yes.
And then, yeah.
Maybe I just add one more. So in the machine learning, in the neural network, what you have here, everything is learnable. But here, we need to choose which one is learnable, which one is not learnable. For example, the raw choice, you have some theta in the logic model. That one can be learnable. And also OD, if you don't know that, you can make it learnable. But link flow, those is from the OD. If OD is known, then those are known. So those are not learnable. So you have to decide which one is learnable and not learnable.
So weight per route, weight per link. So everything is, the process of optimizing weight is always the keep validating with the build data. Right?
Yeah.
So,
Yes.
but the question is there another, another try to optimize that weight by comparing the data from simulation, like a simulated data? Because sometimes, having build data is not so easy. So maybe in the back end, so simulation is running, and then we catch the data and then comparing with them. So training rate is there.
I see. So I guess what you are talking about is a forward path can be a simulation, and then you compare with the data. So the issue here is actually the simulation is actually not differentiable. So it's a black box too. In most of the cases, black box. And because it's not differentiable, then it's difficult to get the gradient. If you don't get gradient, then it's difficult to directly recalculate the weight. So that's an issue. So there are actually several papers that try to linearize the simulation. So basically you have to do something for the simulation to make it more analytical. And after that, you can put that into this computational graph. Actually, the paper I wrote is about this. So this one, because it's a dynamic OD estimation, so that means you have a dynamic simulation behind it. So what I did is I have a linear approximation of the current simulation status, and then you can calculate the gradient and the output. But it is always a difficult problem because it's a black box calculation.
Questions? Other questions?
Wait. In the network, basically things, it has to be learned from the data. The data means the historical data.
Right.
So what if you wanted to investigate new road, new bridge in 5 years' time?
I see.
Is that possible to somehow to transfer some learning?
Yeah, so in machine learning, we call it transferability.
Yeah.
So here, so in the traditional transport planning community, what they did is, as long as they have a model that can replicate the current situation, then they believe that the choice model and the link performance model, those are transferable.
Yeah.
And then they just rerun the model in the future. And then they believe this will predict the future. So they don't talk about transferability. They basically, the question here is that you can see from this figure, this whole problem is that we are underfitting, we are not overfitting. So this is actually directly feeding to the training data. We are not doing the training testing because it's not meaningful. Currently, the issue is that we cannot do overfitting. Even, for example, I just run a simulation. I want to make the simulation exactly the same as the real world. We cannot do it. We cannot do it means that we cannot overfit. Then it's difficult. So at this stage, it's difficult to talk about transferability.
Actually, I have another question. This is my pure curiosity from one of my research projects that I actually have to make a solution for that. In this kind of problem, the one assumption is vehicles can drive any link in anywhere. There's no any specific link that not allowed for driving. But you know, if we think about that in the city center, there are just normal vehicles, and then electric scooters, and then maybe delivery robot. So there are different types of vehicles, and some specific vehicles can be driving on specific links, but let's say a delivery robot cannot just go outside some area and it's not allowed to driving on a normal road, right?
Yeah.
But let's say we are trying to make multiple routes for multiple vehicle settings at the same time, then so do you have any idea how to solve that thing? Is that just like adjusting link cost function?
Right, there are actually some approach to do this. So in network modeling community, what they have is, we call it a super network, meaning that you have different layer of the network. For example, you have the row layer and you have curve space layer. And for example, the scooter is actually maybe it drives on the curve space.
Yeah.
So in general, you have multiple layer of the network. And that's actually, if you're using OpenStreetMap, they also have multiple layer. The issue is that you have to connect those networks using some connecting points. So for example, the road and the curve, the connecting point is actually whether you can go down. And also, for example, we can also have another layer. We can also have some link property, which is restrictions. For example, this link, you cannot have scooters or you cannot have trucks. It's doable, but the model will become more complicated. So it's in the network model community, they call it multimodal traffic assignment. Something like that.
Okay, so there have been such kind of try.
Right.
in the
Right.
previous
Especially if
days.
you're talking shortest paths, they definitely consider all those restrictions. They have a solution algorithm for this multimodal network.
Okay, sounds good. Yeah. Thank you.
Thank you.